Okay, we started talking about DC to AC bidirectional converters, okay, that can be employed to drive AC motors, and they are known as the inverters. Okay, so we are talking about inverters. We started to talk about the one-phase sinusoidal pulse width modulated inverters. Okay, so we started to talk about what is also called the linear region of a pulse width modulation. Okay, so we start to talk about, let's say, if you put in a plane the amplitude modulation factor MA that ranges from 0 to 1, and we have here the output fundamental component of the inverters, the situation that, say, occurs when MA is limited from 0 to 1. Okay, and we learned that the peak value I can change, I can modulate, can control or regulate the peak amplitude of the fundamental component of the output, changing the MA factor from 0 to VT. Okay, and MA is simply the ratio between the peak-to-peak value of the control voltage with respect to the triangular volt. So we can say that this is 2 times the amplitude of the sine wave used for the control voltage. Okay, so which is our basic topology for building up inverters is the standard 4-quadrant switch mode converters. Okay, so you have here the H bridge or full bridge, in which you have 2 legs in parallel. From one side you have a voltage which is constant, VD, and you have a capacitor CD. Then you have the leg A, in which you have 2 switches. Okay, so TA plus and TA minus, and 2 diodes, DA plus and DA minus. And this is the node A. Then you have the second leg, which is the leg B, and then you have the same, say, construction made up by transistor TB plus, TB plus, TB minus, DB minus. Okay, and this is the node B. From the node A and the node B, you can have your load. So you have the inductance L, and so you have the current I naught and the voltage V naught. Okay, and to this side, which is the current side of this bidirectional 4-quadrant converter, you can apply, you can connect your motor. Okay, up to now we are considering the linear pulse width modulator, which is also called sinusoidal PWM application. This is a one-phase inverter. Okay, it's not a 3-phase, so it is used for say driving one-phase AC motor. Before continuing, starting from this point, I want to answer to a question that I received by email. Okay, and the question was about the state of conduction of transistor in a 4-quadrant converter like this one. Okay, I want to be, let's say, I repeat something that I already explained, but maybe I can say in a way which is more clear. Okay, so this is my converter in which I put just switches instead of transistors. Basically, you can use a different kind of transistor, but for the range of application that we are concerned, so say application in the low power up to say 1 kilowatt, more or less, basically two kinds of transistors are currently employed that are IGBTs and power MOSFETs. Okay, there is a little difference in the conduction of these two kind of transistors. Okay, so if you have MOSFETs, it happens that when the MOSFET is on, so when the voltage across its gate and source port is higher than a specific threshold, let's say from 4 to 6 volt, typically for power MOSFET, the transistor conducts current here to the drain, but this current can be bidirectional. Okay, so the current here when the MOSFET is on can be, let's say, in this direction from the drain to the source, or also in the opposite direction. Okay, when the MOSFET is on, the channel is formed, let's say, into the body region of the MOSFET, and this channel can be the path for current flowing in both the direction. When the MOSFET is off, so when the voltage VGS is lower than the threshold of the MOSFET, so the MOSFET is, let's say, basically an open circuit, then you have to think about of the body diode. The body diode is intrinsically inside the MOSFET due to the construction of the MOSFET. Okay, it's not something that you can add. Of course, this diode is not, let's say, designed to be a diode, something that you have for free in the construction of the MOSFET. Okay, so maybe this is not optimized for fast operation. Okay, but anyway, you can use this body diode, and the body diode can be used, for example, for, say, conducting a current in this direction when the MOSFET is off. Okay, for IGBTs, we have to consider that there is no intrinsic bidirectionality. And so when you have IGBTs, okay, and the IGBTs is on, meaning that the voltage between the base and the gate and the emitter is higher than a specific threshold, more or less the same voltage level that you can have in the power MOSFET, 4 to 6. What happens is that the transistor, the IGBT, can only conduct current flowing from the collector to the emitter in this direction. You cannot have the bidirectionally featured of the MOSFET, of a conducting MOSFET. What happens when the IGBT is off? But when the IGBT is off, so when the voltage VGE is less than the threshold, there is no possibility to make a current flowing because the transistor basically is an open circuit. So you have to add something at the external side. So that means that you have to put a diode. There is no body diode intrinsically, there for the construction as it happens for MOSFET. Something that the manufacturers have to add in the same package of the IGBT. They are called copac. Copac means that they are simultaneously present in the same package. Okay, so maybe this diode is a little bit more optimized for fast operation because this is specifically constructed. But basically, the operation is the same of the body diode. It means that when the IGBT is off, it can make flow current in this direction. So just to give you an example, we know that there is a, say, possibility configuration of the switch, for example, in which TA plus and TB minus are on. In that specific configuration of the switch, the output voltage V naught is equal to VD. This is the state of the transistor by which they are on or off. This is not the conduction state. So it give us no information about which devices are practically conducting the current. Okay, so which way I can understand which device that conducts the current depends on the direction of the current. If the current I naught is positive, okay, so it flows exactly as indicated in the figure here, the device that conducts the current, since TA plus and TB minus are both on, are TA plus and TB minus, independently if they are IGBTs or MOSFET. Okay, because the current flow into there as the right, let's say, direction. This one, it goes here, becomes positive, goes into the load here, and return back there. Okay, so what happens if the current is negative? If the current is negative, so the current flow in a direction which is, let's say, opposite to this one, so the current flow in this direction here, what happens? But basically, the situation is different if you have IGBTs or MOSFET. If you have IGBTs, there is no possibility that the current can flow from the, say, the emitter to the collector in this direction here. So in that case, the current flow through dB minus and dA plus if you have IGBTs. What happens if you have MOSFET? But MOSFET can support current flowing from the emitter and collector when they are on, like in that situation. And so it is TA plus and TB minus if you have MOSFET. We are changing the, let's say, switching strategy? Absolutely not. The switching strategy is always the same. I have TA plus and TB minus on. What is different is the role of the different devices in conducting the current. Okay? So there is no different switching strategy, but you have to think that the current flow in different devices. I hope that this answered the questions, and this can be, say, clarify a little bit what I explained in, say, previous lectures and answered the questions. Is here the student Cianciulli that asked me this question? Okay, he's not here. But anyway, he can say follow the my answer here, and I think that this is answer that maybe is interesting for some of you. Okay, so what we learned in the previous lecture, that basically, since this is a 4-quadrant converter, that we have the standard 2 different way to modulate switches that are the bipolar pulse width modulator and the unipolar pulse width modulator. Okay, so let me just consider, for example, the unipolar pulse width modulator. Remember that unipolar pulse width modulator, you have the following different state of the transistor. Say we have TA plus and TB plus on. That provides you, let me put here the output voltage and also the basically the output voltage. Okay. The output voltage is null when you have both I-side transistors that are on. Then you have TA plus and TB minus on, and then you have VD, and then you have another condition which is TA minus TB plus on, giving you negative VD, and then you have another stage in which you have 0, which is TA minus TB minus, giving you 0. Okay, basically you have these 4 switching condition for unipolar pass width modulator, giving you 3 levels: 0, negative VD, and plus VD for, say, the output voltage. Let me just consider what happens to the input side. So what happens, for example, here to the current, let me call this current ID. Supposing that the output current, suppose that you have here a generic load, the current here is positive. I naught is positive, okay? What happens to the current ID? When both transistors TA plus and TB plus are on, it means that you are in this situation. Okay, so basically the current recirculate in this mesh here, depending on the kind of transistor you are using. It can circulate through diodes or MOS or the transistor itself, but not important. What happens is that you have this kind of recirculation here. What happens to the current ID? Well, the current ID basically is null. We have no current there. Okay. What happens when you have TA plus and TB minus on? In that situation, you have this case. Okay, in that case, the current flow following this path. Okay, so the current ID is the same of the current I naught. What happens when the opposite occurs? So when you have this transistor open and this Q1 closed, and the current is positive or negative, is always the same. If the current, for example, has this direction here, the current flows in this way. Okay, here, if the current is negative, the same. Say, basically, it happens that ID is always negative I naught. What happens when these two transistors, A minus and B minus, are on? The current will circulate here, no current flow to, say, the input side. So if you look at the current flowing at the input side, okay, you can see that, again, you have 3 different levels. Okay, you have 0, negative I naught, and positive I naught. Let me just consider, say, the graph of the output voltage, V naught and I naught, supposing the average value, okay, something like this. This is V naught, averaged, so this is the fundamental component of the output voltage, so something that you can obtain after filtering out the voltage V naught appearing here. And since the load typically is an inductive ohmic law, the current lags the voltage. Okay, this is the current I naught averaged. Okay. You also know that all my activities depends on a switching interval, so you can have something like this. Each of these intervals, let's say, is a time frame in which you have a different combination of the switch like this. Okay. So, for example, what happens? that when you have, let's say, TA plus and TP plus on, it happens that the output voltage is null and the output current is and the input current is null. So if I want to drive, so I want to say draw this the same slide here in the same plane, the current ID, okay, the current ID is the same of the current I naught when you have this switch combination. Is something that is opposite to the current I naught when you have this TA minus TB plus combination, and is zero in the other two situations. So you can have something like this. For example, it can be zero here, or it can be equal to I naught here, zero, I naught, zero, I naught, zero, and then here you can have, say, this is the current is negative, so this means that you have negative I naught, zero, negative I naught, zero, etc. So you can see I have something that is, say, something like this. So you have a behavior of the current, which is something like this, okay, ranging three different levels. Negative I naught, zero, negative I naught, or say plus I naught, zero, etc. While you have this behavior negative I naught or plus I naught, because negative I naught is only reached when you have this combination, okay? And this combination is only possible when you have negative current at the output. So in this, say, interval here. So when you have negative current, it happens that the state alternates between 0 and negative I naught. When you have positive current, here the states of the current of the input current alternates between 0 and plus I naught. So the behavior of the input current is to be something, let's say, switching in this way, having, say, a frequency of commutation, if you want, that depends on the time frame which each of these different combination of the switch occurs. The same happens for the bipolar pulse width modulator. For the bipolar pulse width modulator, bipolar PWM, the main difference is that you have just two different, say, combination of the switch that are TA plus TB minus on or TA minus TB plus on. And the output voltage has just two different voltage levels, positive VD, negative VD. Okay, what happens to the current ID? But the current ID is equal to the current I naught when TA plus and TB minus are on. So basically, this is the state you have here. Or it is negative I naught when TA minus TB plus are on. So if you remember in which way you can switch this status, between these two different status, you can see that if this is the output voltage and this is the output current, and then you have different T-switch intervals that I put here and say approximate wave, the current can reach in the input side ID current. ID is blue, is, say, for example, here could be I naught, or can be, for example, here negative I naught, I naught, and negative I naught, I naught, negative I naught. So it is negative positive I naught, plus I naught, negative I naught, etc. You are alternating these two different states. And this is what you can see on the input side. Okay, basically this is what you can see. So the same levels that you can have for the output voltage, you can see appearing at the input side for the current ID. The current I'm plotting for in blue is the current, say, supplying the full bridge here. Okay, it depends on the switch, on the status of the switch. Of course, you have more status of the switch in the full bridge for the unipolar pulse width modulator, because you have TA plus and TB plus, or TA minus and TB minus, that gives you the zero level here that you have here. It can be, say, informative. It can be instructive to look at the DC side current in the bipolar switch modulator. Okay, something that I just looked here, I explained here. This is the instantaneous expression, but we can elaborate a little bit this waveform, okay, in order to see a specific characteristic for this modulation scheme. And in order to do this, so let me just put here for bipolar pulse width modulator, the DC side ID current. In order to, say, for the sake of simplicity, I want to a little bit simplify the analysis because it can be tedious. But maybe the results that we can obtain by simplifying a little bit the discussion are the same that you can have for more complex and circuits. Let me consider this specific situation for our inverter. You have this inverter, which has, say, set of control signal. Okay, you have here basically the full bridge. Okay, this is the current ID because this is the DC side, and you have here the filter at the output. This is the capacitor at the input. My hypothesis here is that we are using a very large switching frequency. So let me put here hypothesis. Basically, this condition can be extrapolated to consider Fs that, say, goes to infinite. Okay. And also suppose that I put here at the output side a low-pass filter to obtain just the average quantities, V naught average and I naught average. For example, this filter can be a second order low-pass filter. Okay, let me put I don't know, LF2, GF2. So here you can have V naught and I naught, and these quantities are sinusoidal quantities. Okay. So basically they are the average value of the output current and voltage at the exit of my inverter. Okay. And then you have here your load. Your load can be, say, a motor, whatever. So this is your generic load. It's not important here. At the input, I'd like to have the same say, say, the same circuit, the same filtering that you have at the output. For example, I can put here a filter, okay, and this low pass filter make possible to have here a current ID star that only includes the, say, basically it is the let's say the average characteristic of the current ID. So this is LF1, this is GF1, CF1. Since the switching frequency is infinite here, or very large, what happens to the output spectrum? If you see the output spectrum, it means that you have the output spectrum, the voltage here. You have the frequency F1, which is the frequency of this output voltage here, something that I want to obtain at the output of my inverter. This is the frequency of the sinusoidal voltage control that you can have here. Okay. Then you have something, let's say, around the first harmonic of the frequency of switch, which is very large. So basically you have a very large frequency space in which you have just F1. Okay, this filter here is something that you want to use for having for isolating F1 with respect to all the higher order harmonics, in order to have at the output just the sinusoidal behavior. Okay, you want to eliminate, to mitigate the effect of the switching frequency and then all the subharmonics, let's say the intermodulation product, etc. Since my switching frequency is very large, I can extract the component F1 by a filter which has a low pass filter, LF2 and CF2, that has a corner frequency that can be very large. For example, a filter like this, okay, in which the corner frequency FC is here, can mitigate the high order harmonics, and at the end of this filter reaction, the output voltage V0 is exactly the sinusoidal at component F1. Since Fs is very large, the frequency Fc can be very large, which is the frequency Fc of a LC second order filter is 2P LF2 CF2. It means that my frequency Fc can be very large. Heat delete can be infinite if Fs is also frequency. And so, to this situation, I can see that LF2 or also CF2 basically are very small. So in this, my hypothesis in which I put Fs with very large, I can filter out, I can demodulate the V0 output voltage here, say just having a filter made by very small inductive and capacitor component. We can exploit this characteristic here. The same can be applicable to the input. To the input side, as I show before, the current has this blue behavior. Okay, something that, let's say, if you look at the harmonic component, for sure you have a component of the switching frequency, because you have the switching here, okay, and this is exactly the switch. So this blue curve at the DC side here has harmonics at the switching frequency. Okay, the switching frequency is larger, so I can use a low pass filter in order just to extract the component you can have in the baseband, so say at frequency lower than a switch, by using again LF1 and CF1, which are both very small, okay, following the same reason that you can have at the output. Okay? So basically, this my abstraction is just to say, consider a situation which is fictitious, it's not real, in which since Fs is very large, you can demodulate the output voltage and also the input current, eliminating all the behavior at the switching frequency, and just, let's say, consider what happened for very small frequency around, let's say, the DC. We know that the output side, these result in a voltage V naught and a current I naught that are sinusoidal. Okay. Now we are interested in what happens during this reasoning for the current ID star, which is the filtered current depurated from the switching FS components of the spectrum. The first thing that you have to consider here that my inverter here is only composed by switches. All the reactive components are, say, put outside my block. Okay, are here, are here, are here, and are here. So in terms of the power which is dissipated by this switch combination, you can see that the power entering here is the same instantaneous power that exiting the block. Now look at the power that you have at the output of, say here, say at the input and at the output of my circuit, including the filters. The output instantaneous power that exits here depends on the fact that you have reactive elements, and the reactive element stores energy. So basically, when you have a situation like this, you cannot say that instantaneous power entering here, for example, is the same of the output instantaneous power P naught, because there are some reactive elements inside that can store energy. But on the basis of my discussion, these reactive elements are, let's say, basically very small. They both, say, tend to be, say, zero. So the energy stored in these very small components here, 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 and here is almost null. So on the basis of this assumption, the results of all these discussions, that we can say that the instantaneous power P in is basically the same of the output instantaneous power. Okay, I repeat myself, when you have reactive elements, this kind of equation is not true, because depends on the energy which is stored inside the reactive element. So you cannot say that at that specific time instant what enters in terms of energy is the same that you can have at the output, because some element stores energy and this energy is not provided to the output, for example. But in that specific case in which the reactive elements are not present or are so small that the energy that they stored is, let's say, negligible, you can say that the instantaneous power at the input is the same of the instantaneous power at the output. Okay, so I'm using this fixed situation for computing the ID star, so the low frequency component of the current at the input side of my inverter. Okay, I hope that this discussion is, let's say, not too much confusing. So P naught is given by what? But P naught is the output voltage, is the output power. So basically is the product of these two quantities here that are the average expression of the output voltage and current. So it is V naught averaged multiplied I naught averaged. And what about V in? But V in is basically provided by what? But V in is, say here you have VD, okay? And so you have VD multiplied ID star. What about V naught averaged? This is, for example, as a peak value multiplied an expression which is a sine wave at frequency f1. What about I naught? I naught is again a sinusoidal having a peak value and a sine wave at frequency f1, but we have also a phase angle because the current lags the voltage. We have, let's say, a phase difference due to the fact that my load is not a resistance. The load is something which has inside, say, inductance, especially if you have a motors. This is the winding inductance. So basically this means that VD multiplied my unknown, which is ID star, is V naught multiplied I naught sine omega 1 t multiplied sine omega 1 t minus phi 1. And so id star is given by this quantity divided by Vd. These appear here. You can have this multiplication. Okay, you can solve this simply by considering that there are a lot of useful trigonometric expression giving you, say, the product of two sine terms like this. For example, you can transform is 1f cosine phi 1 minus cosine of 2 omega 1 t minus phi 1 in this way. And so id becomes v naught over I naught divided vd multiplied 1f coming from this 1f here, cosine phi 1, and then you have another terms which is 1f v naught peak I naught peak divided vd. Then you have a cosine of 2 times the frequency of 1, so cosine of 2 omega 1 t minus f1. Okay, so basically you have that id star, which is the low frequency expression components of the current flowing at the input current side of the inverter, is the sum of one contribution, this one, which is basically constant because this is the product of constant quantity. So this is a totally constant quantity. And then you have minus a current, which is ID2. It's a current that switches at twice the frequency F1. So ID star is equal to DC component minus an IC component switching at twice the switch frequency. So this is as a frequency of 2 omega 1. And this is DC. If you look at the at this expression, okay, so okay, you have here ID star, which has a DC component plus an AC component at 2 times omega 1. Remember that VD is constant. So the only contribution that provides you positive power, so real power, say providing energy to your inverter, is just given by the DC component of the current, because the voltage is a DC. If you want to consider the power, the average power provided by your input source, this is 1 over T of the integrals between the product of the voltage and the current, okay? And since in our case, this is VD, is the input side, this integral is not null, the integral is different from 0 only for DC component of IT. So it means that the contribution that provides you real power to your SiC is just given by this part here. Okay, while this contribution here is something that does not provide any useful energy contribution. It's something that basically can lead to losses, okay, because this is a current that can flow into the wires and that can have ohmic losses, and so this is something that is not good. Okay, let me just to see you graphically the behavior of this current the waveform of this current. This is something that I have in the, I put in the slide. Okay, so let me share the slide. Okay, here you can see the same discussion that I made before. Okay, you have the expression of the output voltage bipolar configuration and the current. As you can see in the second drawn here, okay, you can see that you have I naught, okay. I naught here is the I naught average quantity, okay, is the sine wave here. Frequency is f1. Then I have ID. This contribution here is the total switching current that I have at the input side. So you can have is something that has behavior as I naught, negative I naught, I naught, negative I naught, etc. So something that bounces up and down, alternating to different situations, okay? And then you can have this current that I have here, ID, as a DC component. So this ID, so this contribution here, DC quantity, constant, plus this quantity here, which is ID2 switching, or say having a, say, sine wave at 2 times frequency, f1. So this is 1. So this is, in terms of low frequency component of this current ID here, you can have, let's say, the summation of a DC quantity plus 2 times this sine wave, 2 times f1 sine wave. The only useful contribution to the real power provided by the source is given by the DC current ID. So this current at 2 times the frequency f1 is something that you have to, let's say, in some way to absorb. And how can you say avoiding this current to circulate? But you can use a capacitor. So let me just again share the whiteboard. Okay. Since this current here, ID, let me put the current ID here, as a DC plus IC component, okay, the only way to avoid the IC contribution to enters my circuit, okay, and providing, say, additional losses, okay, is to put here a capacitor, and this capacitor helps in absorbing just the AC contribution here. So basically now the ID contribution that I have here is only DC. So the filter that you can have here, so basically this capacitor here, should be, say, designed in order to absorb this AC current flowing from the input side, which is the peak value of this ID2 current here. The peak value is this characteristic here, this voltage here. This peak value, just let me put in this way, ID2 peak is 1F V naught peak I naught peak divided VD, flowing into a generic impedance provides you a voltage drop. Zeta C is a generic impedance to which this current can flow. If I have as an impedance, say, impedance of a capacitor, this is omega C. This current has a, say, variation that follows 2 times F1. So it is basically, it is important to understand which is the impedance of this capacitor at the frequency 2 omega 1. And so this is 2 omega 1 multiplied C. So at omega, which is equal to 2 times omega 1, which is the frequency of this current, you can have that VD2 basically is 1 over 2 times omega 1c multiplied ID2 peak to omega 1c multiplied 1f V naught I naught peak VD. So it is V naught peak I naught peak divided 4 VD omega 1c. This is VD2 peak. For example, you can now design C with the aim to limit this voltage peak across the capacitor C. So for example, if you have that VD2 peak should be less or equal to a VD2, say, desired value, very small, say I don't want to have a very large ripple across this capacitor, then you can say that C should be larger than V naught I naught for omega 1 VD multiplied this VD2 desired. I don't know, this can be again a few percent of the voltage VD. For example, if voltage VD is, I don't know, 100 volt, you can admit 1 volt. And then you can put here, then you can have an expression for a value of this capacitor, for example. Of course, this is the only way to design this capacitor, okay? The capacitor C, or say this is the gain, the same of the capacitor CD we put at the input, can be also chosen and designed for other, say, different, performance. For example, this can be the capacitor that you can have at the output of a first stage, for example, a rectifier, where that was main purpose is to rectify the AC voltage into the DC voltage. So this can be the filter output capacitor of a rectifier. So basically, this capacitor should be designed merging the different kind of requirements it may have. For example, also this one. So you can have a capacitor larger than several different conditions depending on what you are considering. And this is one of the conditions you have to respect for bipolar pulse width modulator. Pay attention also to the fact that any real capacitor is not an ideal capacitor. Okay? An ideal capacitor like this, for example, has an impedance that basically is 1 over omega C. This is 1 over omega C. So it's something that in terms of frequency reduces itself with a slope of negative dB decade. But practical capacitor always have parasitics, like for example inductance and resistance. So you have what is called the equivalent series inductance and the equivalent series resistance. In that situation, the behavior of the capacitor can be different in terms of impedance versus frequency. For example, can be something like this. So it acts like a capacitor just in this range up to a frequency which is, let's say, the resonant frequency, 1 over 2 P ESL multiplied C. And then it acts like an inductance over this value. So it is important to understand that if this capacitor should work well for up to this frequency here, that my resonant frequency should be higher than omega 1. Okay, this for a ceramic capacitor. If you have a, say, electrolytic capacitor, then the behavior is something which is basically a little bit different from this. This is for ceramic capacitor that basically have no ESR. If you have an electrolytic capacitor, then the ESR is very important parasitics. And so the behavior of the impedance versus frequency is something like this. Is as a ESR here, so it behaves like a resistor, like a capacitor, and like an inductor. Okay, you want that your behavior is something that is, let's say, around here. And this frequency is, let's say, depending on the application, can be kilohertz, 1 to 10 kilohertz. So then typically then you have to face something which is, let's say, a little bit more practical instead of using this characteristic. Okay, if typically for application that a standard application F1 is in the range, as I listed some, say, standard application which F1 can be 50, 60 or 400 hertz. Okay, and so that means the 2F1 at the maximum could be something which is less than 1 kilohertz. So you are effectively operating your capacitor here. If you are operating the motor, your RC motor, for a fundamental component which is a little bit higher, there are, for example, ultrasonic motors that can be operated at, say, with fundamental frequency higher than kilohertz. That in that situation, maybe different strategies can be adopted to filter out these 2F1 component of the input current. Are there any questions about this discussion? Something which is not clear? Something that maybe I have to repeat? No? So just let me to discuss a little bit again on the same topic, which is the sinusoidal or linear pulse width modulator. For example, that time remember what the time is that small time interval t delta, that time or blanking time, something like this, that you have to insert between, let's say, the switching action. Okay, typically this is inserted in order to delay a little bit the turn on phase of a switch, to avoid the simultaneous cross conduction of two transistors in the same leg that effectively could short the input source. Okay, and then you can have permanent images of your full bridge. That time should be sized according to the switch you are using. Okay, so if you have a very slow switch, that time should be, say, tailored to this large turn off or turn on time. If you have fast switches, like for example MOSFET, then you can have a shorter that time. But basically what happens is that we already studied the behavior of the time for a full quadrant converter. Okay, and I can report here the previous result. You have that the variation of the voltage delta V naught, which is the difference between the ideal minus the real situation. So the ideal means that you have T delta 0 versus the situation which you have inserted T delta here, is something that depends on the direction of the current. So for example, you can have 2 T delta over Ts, which is the switching frequency, multiplied Vt, when the current I naught is positive, and negative 2 times T delta Ts multiplied Vt when the output current I naught is negative, okay? Of course, we can use the same result of 4-quadrant converter, because basically our one-phase inverter is a 4-quadrant converter, so we can apply the same results, okay? Which is the difference here? The difference is that look at the output voltage and output current, V naught, I naught. V naught average and I naught average. You have something like this. This is the output voltage. And then you have the current. Since the load is a ohmic load, the current is a little bit delayed. Something like this. So this is I, the current. So we have a region in which the current is positive, like for example here. Okay, here the current is positive. And you have region in which the current is negative. This is the output voltage, but the output voltage depends, in case of insertion of the dead time, depend on the direction of the current. For example, you have that when the current is positive, so you have this case here. When the current is positive, the difference between the ideal and the real is that you have a positive quantity. So it means that you have a output voltage which is a little bit less than this. Okay, so this is the V naught voltage with T delta different from 0. Okay, while this is with T delta 0. Okay, so this is the real case. What happens when the current is negative? But when the current is negative, so you are here, you have this negative sign here, meaning that the real case, so the case in which you have T delta, is brings to this situation, to a different case here. Okay, so if you look in a period of your output voltage, you can see that you have, say, this step here, because the output voltage, say, it can be lower or higher depending on the direction of the current. It's like you have, if you think at this situation of the real, say, the real case, the ideal case of the voltage, like this, plus something added to it, and this is little bit exaggerating, but this is something like this. Now, if you add these two waveforms, in which the second one is just a rectangular waveform having a period of exactly this is T1, okay. Basically, you have the summation of the two. So, if you want to look at the spectrum, okay, what happens? That if you look at the spectrum of this one, the spectrum of a rectangular waveform like this is something that has, let's say, F1, so 1 over T1, and we have 3F1, 5F1, etc. This is the standard spectrum of a rectangular waveform having period T1. So you have the odd harmonics of the fundamental, which is F1. The overall spectrum of the real current, so this one, is not exactly the summation of the two spectra. okay, because it's something which is, say, something a little bit different. But anyway, if you look at the spectrum of T delta V naught, you can see that you have F1, then you have harmonics, odd harmonics that results basically from these steps here occurring at, say, with the frequency of T1 here. And then you have the standard harmonics of the sine wave. So you have Fs, then you have intermodulation products, etc., etc., etc. So the presence of these other harmonics that basically you don't have if you have the ideal situation with delta equal to 0, have an impact on the filtering effect at the output of my inverter, okay, the demodulation effect that you need in order to get at the output just F1 and not you have all the high order harmonics, because now you need a better filtering action here in order to eliminate harmonics that are much closer to F1 than, for example, F switch, especially if you have MF, which is much larger than 1, so Fs very large than F1. This block here, intermodulation product around Fs, is something that can be made, let's say, very far away from F1. Okay, now that time introduces these other harmonics, then it can be, let's say, a little bit different from this. But basically, this problem can be solved by adopting specific control strategies that mitigate the output voltage difference, eliminate basically the behavior I have here. Okay, so there exist specific solutions in terms of better control action of the output voltage that may be exploited to reduce to very low level these harmonics here, all the other harmonics F1, and then to avoid this kind of, say, filtering and demodulation product of the output. Basically, the problem exists. Questions, doubt, something which is maybe is basically I have to repeat. I want to continue this talking about the one-phase inverter in linear application, so the linear pulse width modulator, sinusoidal pulse width modulator, just considering, for example, the how to choose the switching frequency, basically. Because this is something that can be, say, useful in this linear application. And it is something which is also related to this discussion I made here. Remember that if I'm using my bidirectional converter in the linear application means that my MA is less than 1. Okay, so I have the control voltage, which now is a sine wave, that has a peak-to-peak value. So the dynamic of the control voltage is always within the dynamic of the triangular waveform, the pulse width modulator. So we are using this as a constraint. Then you are in the linear situation. Okay. In that case, I'm using the comparison between the sine wave and the triangular carrier wave inside the modulator to, let's say, traduce the information of the control voltage, basically the frequency and the amplitude of this control voltage, into the into a variation of a pulse width. Okay, is a translation of the way I can, let's say, communicate my my information, okay? The information which is within the amplitude variation or the frequency variation of the control voltage now becomes a variation of the pulse width modulator. Is the pulse width modulator duty cycle, basically, okay, that changes according to the sine wave variation of the control voltage. So I'm using this, say, translation in order to drive my full bridge. The information is basically is amplified linearly. So I have the same information content at the output. So basically I have the same spectrum amplified at the output. And then I have to, let's say, demodulate in order to extract exactly the information I need. This is basically my linear, say, process, okay? Modulation, amplification, demodulation. Okay? I saw this several times. And in order to do this, I have to respect Nyquist theorem for a correct reconstruction of my original information. So Fs much larger than F1. So in other terms, the frequency modulation factor should be much higher than 1. Okay, something that I said here. So I choose as the switching frequency? Something that I can choose, say, is a degree of freedom, or basically is something that depends on, for example, on the semiconductor switches, on the devices that I'm employing as switches. Look what happens, for example, for the higher power level application. Let me consider the higher power level something which is higher than hundreds of kilowatts. So something that we'll not see in this course, because this course is just for very low power level, say less than 1 kilowatt. See? Because electronic circuits are employed typically for this kind of applications. In that case, basically, you are not allowed to use, for example, IGBTs or MOSFETs, okay? Because they cannot handle the very large power level that is required in the application. They cannot handle, for example, very large level of current. That means, for example, kiloamp or tens of kiloamp, okay? Something which is not possible. So no IGBTs, no bipolar transistor, no power MOSFET. Typically, what is employed are the silicon controlled rectifier, SCR for short. They are basically in the we are in the realm of the thyristors. They are thyristor devices that I'm not going to consider in this course, okay? But they are very basically very bulky devices that are able to manage this very large power level. The drawback of this kind of thyristors, not transistors, thyristors, is that they are very, very slow. Okay, so very slow means that you cannot operate them at kilohertz. Typically, they are so slow that you can operate at frequencies that are lower than hundreds of hertz. Basically, they are operated at the frequency of the mains, 50 hertz, 60 hertz. So this is the typical frequency of application. So this is basically the switching frequency that you can apply here. Okay, and since it's the switching frequency, okay, remember that Fs over F1 is my frequency modulation factor, and this should be very large. Okay, this means that this is 100 hertz. As I said before, F1 is typically 50 hertz or 60 hertz for, say, the mains application. So it means that this MF here is in the range of unity. MF is, I don't know, 2, 3, no more than this. they are typically very, let's say, complicated to filter out, okay, because the high order harmonics at the output voltage spectrum is very close to the frequency F1, because there is no clear separation in frequency between F1 and Fs. So filtering this kind of, say, application, it could be very, very complicated, or basically you are using these for application in which you are not so interested in the quality of your output sine wave, okay? Or you can admit some ripple in the current or ripple in the torque, etc., etc. So complicated to filter out. Harmonics. Let me move to the average. Power level. This means, let's say, hundreds of kilowatts, so less than hundreds of kilowatts up to, I don't know, units of kilowatts. Okay. In this case, typically, IGBTs are employed. Okay, IGBTs in this field are progressively replacing bipolar transistor in application in these fields. Okay, from sorry, this is the power unit of kilowatt, some unit of kilowatt to hundreds of kilowatts. Okay, IGBTs are most employed. IGBTs have the drawback is that they are very slow when they are commanded to be turned off. Okay, so the turn off is slow, and typically they are operated at frequency that are in the range of tens of kilohertz. Even this, say, limit is increasing due to the better semiconductor technology solutions, etc. But basically, this is the range. Let's say 20 kilohertz is the, say, typical application of the switching frequency. In that case, MF is, I don't know, Fs over F1 is, in the case F1 is 50 or 60 hertz, so you are considering the standard application for these AC motors operating at fundamental, let's say, in the 100 of hertz. This means that this is in the range of hundreds. That can be 100, it can be 200, something like this. So as you can see here, the situation is a little bit easy for filter out these high order harmonics, because now the separation between the F1, which is the frequency you want to get at the output, and the switching frequency is, let's say, something that can be managed by low pass filtering. Low power level, and this means typically 100 unit of kilowatt. Okay, the basic semiconductor device that is typically employed as switches is the MOSFET, power MOSFET. The power MOSFET is a very fast device because typically you have just to charge and discharge parasitic capacitance with MOSFET. That can be done in easily for frequency that are even in the unit of megahertz or less, 100 of kilohertz, but you can say that from 100 of kilohertz to unit of megahertz. So this means that MF for application in which F1 is 50 or 60 hertz, so 100 of hertz, 400 hertz, this is, let's say, I don't know, it could be higher as 10,000. So in that case, Basically, what happens is that the filtering out is so simple that you can use typically the filter that is made up simply by the circuit of the actuator you are driving. The all air components, equivalent components of the winding of the motor you are driving, by itself acts as a low-pass filter that can be able to use this. But basically, this discussion to consider the fact that the switching frequency you are using depend on the power level you have in your power in your application. Okay, is a nonsense to choose for FS of megahertz if you're using transistor, as I said before. Okay, because it's not possible to act in this way. So I can stop here. We can continue this discussion. Okay, starting from what I finished to say now, tomorrow at 11:30. For the people, for the students that booked their seat today at 2:30, there will be the lab. Okay. If you have question, of course, I'm here to answer your question. Okay, it seems to me that no question from you. So I'd like to thank you. See you. Have a nice afternoon.